I'd like to talk about model error compensator for adding robustness to existing control systems. My name is Hiroshi Okajima from Kumamoto University, Japan. This QR code shows a website for explaining the model error compensators. Various MATLAB codes and links for documents are located in this site. The conference paper is 8 pages. This is the basic structure of model error compensator that adds robustness for existing control systems. P is plant, including model error and disturbance. PM is model of the plant. D is error compensator component. The effect of model error is suppressed by this simple form. This is an outline of this presentation. At first, I talk about background of this research. In control system design, model-based control is widely used. As example of the model-based control, optimal regulator, model predictive control, nonlinear control are used. If we obtain appropriate model of the plant, it is easy to design controller using existing methods. This slide shows a design sequence of model-based control. At first, mathematical model is derived using input and output information. Then, the design controller for the obtained mathematical model. At the last, apply controller for the control system with plant. If good model is obtained, the desired output is achieved for the control system. On the other hand, the desired output cannot be achieved if gap between plant and model exists. To overcome the demerit of the standard model-based control, the robust control is addressed. The controller is designed for a set of models. Conventional robust control involves control for a set of mathematical models. Specifically, a good controller is designed for all models in the set. This means, in other words, that the controller is derived such that the best results are obtained for models of the worst-case plant. As a result, the control response tends to be slower. Another disadvantage is that the admissible performance indices are limited because the problem is more complex. Thus, for each of these, there are advantages and disadvantages. In contrast, our research is considering a new compensator that compensates for errors in the plant for model-based design and add robustness to existing control systems. The aim of this research is to improve robustness as an added value while preserving the good points of model-based control. The bottom figure shows the research objective of our research. In model error compensator, the controller is assumed to be given, and the model error effect is compensated by our method. This is an initial paper about model error compensator. This paper is published at 2013. This slide shows a research history of model error compensator. The left list is our research history and right is by other research groups. Contributions in this presentation is as follows. One is that we summarize research about MEC. Second is we organize how to add MEC to existing systems. Third is we show advancing result of MEC for nonlinear systems. Then we show fundamental structure of the model error compensator. This is the formulation of plant. P is the plant and U and Y are input and output respectively. P is composed of nominal model PM and uncertainty delta P. Delta P is given by multiple of PM, W, and delta. When we consider feed-forward control for the plant P, this block diagram shows the input-output relation. TD is the desired transfer function and the output is given by Ym plus delta Y. There exists error delta Y caused by delta P. In our framework, feed-forward control with model error compensator is given like this. Model error compensator compensates the negative effect of delta y. Design H for achieving small set of model error and small delta y is obtained. This is the structure of model error compensator, which include plant and plant model and error compensator. The input-output relation is given by PC. The transfer function of PC is given by this equation. If PC equal PM is satisfied, make with existing control system act well. Desired function in make is shown in this slide. At first, we want to minimize the model error effect. It is desired that PC equals to PM. It is better to minimize PC minus PM. The transfer function of PC minus PM can be given like this. We can find that if delta P equals to 0, PC equals to PM holds. Then, this factor becomes smaller by high-gain compensator D. This is another desired function in MEC. Robust stability of the feedback loop is characterized by this inequality. This is the case of SISO system. In this slide, design problem of D under the sensor noise environment is shown. It is better to minimize the difference between PM and PC by this equation. To minimize this factor, high-gain compensator is required. On the other hand, if noise are large, high-gain filter gives negative effect. If we want to consider the case that includes not only model error but also noise, such problem can be regarded as a kind of mixed sensitivity function problem. This slide shows an application example for PID control system. Upper figure shows a plant with PID controller. Then, we apply MEC for the PID control system. By using model error compensator, the model error effect is suppressed for the system. This is the case of stable plant, and this is the case of unstable plant. This slide shows closed loop systems. Upper slide shows the case without MEC. Left figure shows the case for stable plant, and right figure shows a case of unstable plant. We can find model error effect in these figures. On the other hand, when we apply MEC for PID control system, we can find the model error effect is suppressed in the case of closed loop system. This is an application example for 3 inertia benchmark problem. This figure shows a board diagram of the system, and it expresses variation of 3 inertial system. We apply frequency-shaped finite state control with MEC. By using this system, we can achieve good performance in the benchmark problem. This slide shows a case of electric wheelchair. This vehicle has 2 motors and free caster. It is difficult to control. This figure shows the slope running using electric wheelchair. Same torques are applied for 2 motors. Then, the electric vehicle turns around. These figures show the case of human manipulating. Upper figure shows the case of flat road, and bottom figure shows the case of slope road. Red dot line shows the case without control, and blue line shows the case of proposed method. We can find human can manipulate electric wheelchair with model error compensator. Then we show about non-minimum phase system and nonlinear system. At first, model error compensator for non-minimum phase system is introduced. This is a case of plant with unstable zero, and this is a plant with delay. Internal stability is wasted by high gain compensator in case of non-minimum phase systems. In our approach, parallel feed-forward filter is applied for non-minimum phase systems. When plant is given like this and parallel filter is given like this, then P plus F is given as a minimum phase system. Also, a case that plant with delay. In this case, when we apply Smith-type compensator and P plus F can be given as a minimum phase system. This idea is applied for model error compensator and the structure is given like this. We can find filter is added to the model error compensator. In our research, we assume Fm equals to F. This is the output result for non-minimum phase system. We add 0 at S equal to 0 for F and pole at S equal to 0 for D. We can find that model error effect is suppressed in case that model error compensator with parallel feed-forward controller. Then, model error compensator for nonlinear system is introduced. Nonlinear plant is given like this. We can find this system is input-affine system. We assume that zero dynamics is stable and F and G are smooth and differentiable. This slide shows a case of conventional linearization method. When there exists no model error, we can achieve linear system by this feedback controller. On the other hand, if there exists model error, this method is not work well. On the other hand, we propose robust feedback linearization method. Tm is the linearized system and U is the feedback linearization method using state of the model. D is the error compensator filter. We can find that the model error effect is suppressed by using proposed method. At the last, we show actual use case. This slide shows a case of make with existing control systems. Left and right show the case that the plant with 1 degree of freedom control system. Left pattern 1 is the method of applying existing control system to the model. Model error suppression performance is make dependent. On the other hand, pattern 2 is a method of replacing the plant with compensated system. The compensated system is considered as a new plant. Which pattern is better is case by case. In addition, we can use various types of control system. This figure shows a case of state feedback, and this figure shows a case of feedforward control. This slide shows characteristics for compared to disturbance observer. In case of disturbance observer, inverse model is required for the system. So in such case, it limits variety of the plant. Inverse model cannot be constructed for non-minimum phase system, many of nonlinear system, MIMO system. In addition, plant P is assumed as stable in disturbance observer. On the other hand, model error compensator is not limited to the stable plant. This is the conclusion of this presentation. The model error compensator is simple and applicable for many systems.